There. Okay, perfect. Thanks, everyone. I'm Krishna Gummadi, and this work is a joint work with my PhD student, Mohammad Bilal Zafar, who is actually attending the workshop as well, and Isabel Valera, who is a postdoctoral student, and my colleague at Max Planck, Manuel Gomez Rodriguez. Now, a little bit of a disclaimer. This is on some topic that we started thinking quite a bit about and working on for the last year or so, but still, I have to confess that I don't fully understand it. But hopefully it will provoke some discussions. So the background for this is, actually John set it up very beautifully. It's about algorithmic or data-driven decision-making. And at a high level, increasingly we see data-driven decision-making assisting or replacing human decision-making in a number of different contexts, from recruiting, where there are startups in Silicon Valley that claim to be able to design automated processing of or screening of job applications better than what humans might be able to do. Of course, in banking, credit ratings and credit risk assessments and loan risk assessments have been around for a long period of time. And in judiciary, John explained these things in great detail. And increasingly, even in journalism, where automated recommender systems are deciding what sort of things you read. Now, if you think about how these algorithmic decisions are made, at a very high level, you're learning from data that were data of decisions that were made by humans in the past, right? So for instance, in the case of a recruiting example, you have a database of users, and each user has some attributes. And then in the past, there were humans who were looking over these users, and they were deciding whether to accept them or to reject them. So these are the kinds of decision-making scenarios that we're considering, where some benefits are given for people with certain records and others are denied. Now, this is something that is probably needless for this audience, but to very quickly go over a very simple type of algorithm or learning algorithms that we're thinking about. Say you have learning linear classifiers, where you have some weights that you assign to each one of the attributes of the users, and then you try to learn a weight vector that would help you make some predictions that match the decisions that were made by humans in the past, right? So geometrically, you would have linear classifiers. You have some data points in some n-dimensional space. The weight vector corresponds to some decision boundary, and then you accept certain user records that are on one side of the decision boundary, you reject them on the other side of the decision boundary. And of course, you always make some misclassifications, and then usually you have some loss function that you define for the misclassification. And then you typically optimize you try to find an optimal weight vector, or the amount of weights, or the amount of emphasis you would want to give on the different attributes of the users to minimize this loss function. Okay, so I'm just racing through these things because this is really not necessary for this audience. But let's come to the real problem that we're interested in, which is discrimination, or the potential for discrimination in decision making. Now, the notion of discrimination is actually a very, very subtle one. It has been very extensively studied in social sciences. There are definitions and theories in political science, moral philosophy, economics, as well as law. Majority of countries today have some form of anti-discrimination laws that cover various different domains. And in fact, discrimination has been recognized in several international human rights laws as well. But what I feel, and what I will try to argue, is that this thing has been studied less from a computational perspective, and that when you start looking at it from a computational perspective, there are some interesting things that come out. So if you were to think about defining discrimination, here is a very, there is no universally accepted definition, even in social sciences communities. But to a first approximation, you could think of a discrimination as wrongfully imposing a relative disadvantage on persons based on their membership in some salient social group. Now, even though that sounds intuitively reasonable, it's actually a heavily, heavily overloaded definition with a lot of contentious debates that go on as to how to determine what constitutes wrong or right, and what constitutes an advantage or a disadvantage, and even what constitutes a salient social group. So these, in social sciences, typically you have a very, you could think of it as a moralized or normative definition, where it is, where you would often end up discussing how to determine various different highlighted features. So for instance, even if you think of a salient social group, you have discrimination that is based on race or gender or things like that, but you don't have discrimination against people with long hair or short hair. So there is a question of, there are debates that are often fought on what feature should be even be considered to form a salient social group. Now, because we're interested in looking at it from a computational perspective, in the talk today, I'm going to consider a non-moralized definition, which is actually significantly more simpler, and where the goal is to actually look at differential treatments of people based on certain features declared as sensitive. Notice that in this non-moralized definition, I've kind of pushed aside all the contentious debates surrounding whether a differential treatment, when is it wrong or when does it constitute a relative disadvantage. And similarly, I'm assuming that somehow certain features are predetermined as sensitive, and we don't have to go into the debates about what constitutes sensitive versus what doesn't constitute sensitive. And the reason to use this somewhat simplified definition is because I feel that hopefully I'll be able to communicate this, that this allows for computational analysis of possible differential treatments, eliminating those contentious questions. So going back to discrimination in decision making, so the really interesting question is that decisions should not be based on some sensitive features. So the attributes that were all the same before, now we're distinguishing between two types of attributes, the sensitive attributes in the red and the non-sensitive attributes in the green. So discrimination to us means there is some sort of a decision making where the sensitive attributes, somehow the decisions are not based on the sensitive attributes. Again, the term based on is overloaded, and that's what we're going to discuss what it would mean in the rest of the talk. So at a high level, there are three questions. The first is, can algorithmic decisions be discriminatory? And then the second is, how can we detect discrimination in decision making? And the third is, can we control algorithmic discrimination in some form? So let's start with and the reason for the last one is, there is this potential promise that if you could control algorithmic discrimination, then maybe eliminating biases would be easier, because it's much easier to control algorithms than retraining people if you knew what that control actually meant. Yeah. So let's start with the first question, can an algorithm discriminate? Well, if you followed the definition of discrimination, of course, yes, because the definition of discrimination has got nothing to do about who is making the decisions, whether it is a human or a machine, but it's based on whether the decisions are based on sensitive features. So yes, you could indeed have a classifier that can make racist or sexist decisions. So if it's trained on biased data, if historical data on job hiring is biased with race and gender discrimination, if you train on it, of course, you're going to be discriminating. So that's the first question is the easiest one. Yes, if it were no, then I would have to stop the talk. But let's move on to the next question, which is a more trickier one, which is how can we detect discrimination in decision making? This essentially means, what do we mean by the word based on, the decisions being based on sensitive features? Now, in some sense, the advantage that we have a little bit here is that there has been a long history of detecting discrimination in human decision making. There have been cases that were considered in various countries for decades now on whether there was discrimination in hiring practices when humans are making the decisions, and whether there's discrimination in housing employment, housing allocation practices and so on. So we're going to leverage some of the studies in that space. So what I'm going to do now is quickly walk you through two tests for detecting discrimination that are frequently used. And then the interesting part would be how could we actually control for discrimination that would come afterwards. So the two tests for detecting discrimination corresponds to a broad categorization of discrimination into two large categories. The first is called the direct discrimination, and the next is called the indirect discrimination. So direct discrimination is something where the decision maker uses the sensitive value or the sensitive feature that is part of the input to make a discriminatory decision. Now, this can be conscious or unconscious, the way in which you can, so an example of a conscious direct discrimination would be you explicitly bias, you have some explicit biases in hiring. In the past, there used to be times when they would advertise positions only for men. An unconscious or an implicit bias is when even if you didn't mean it, you subconsciously actually end up offering different positions for men and women. This is because you somehow recognize that as part of the input. Now, the test for detecting direct discrimination is actually situational testing. So this is the way you would conduct this test is you would give two inputs where in terms of the non-sensitive attributes, they are exactly the same, but you just flip the sensitive attribute and you see if you get different results. Now, this is, of course, if you are able to give the inputs yourself. There may be cases where you're not capable of giving different inputs, but you're analyzing some data from the past decisions, where you could look at two users with very similar non-sensitive attributes. That means in the non-sensitive feature space, they're quite close, but then they're being treated differently, just because they are different in the sensitive attribute space. So this is a test for detecting direct discrimination. So the next broad form of discrimination is indirect discrimination. This is a much harder one. This is at an intuitive level. Again, there can be both conscious and unconscious forms of this. These are situations where you intentionally or unintentionally try to bias the decisions against some group of people by weighting the features that are correlated with a group much more. For instance, if you wanted to suppress, so for instance, these days there is debate about voter ID laws in the US, which Democratic Party members often accuse that Republicans are pushing them to actually intentionally manipulate and suppress the African American vote because they have statistically fewer voter ID cards, kind of a thing. Now, again, there are extensive debates one can have about these things, but let's talk about how can you detect indirect discrimination. Now, this is where all hell breaks loose. This is incredibly hard to detect because sensitive features are not directly used in decisions. So the kinds of tests that people and the courts even applied are proportionality tests over outcomes. That is, are the outcomes for men and women disproportionate? Another way to think about this is the conditional probability of men getting selected and women getting selected when they apply for a job, is that different? And this is codified in laws in many countries. For instance, in the US, there is a doctrine of disparate impact, which considers practices as illegal if they have a disproportionate adverse impact on the persons along the lines of protected trade. Now, the question is, what constitutes disproportionality? Now, in the 70s and the 80s, some US courts applied 80% rule for employment practices, and what this means is, if you look at the percentage of male applicants that got selected and percentage of female applicants got selected, and if 50% of the male applicants get selected, then at least 40% should be selected. Now, of course, different countries and just different jurisdictions use some different measures of this proportionality. So, for instance, if P1 is for one class and one group of people, and P2 is for another group of people, UK actually uses P1 minus P2, EU uses 1 minus P1 by 1 minus P2 in its anti-discrimination laws and so on. Now, of course, the exact threshold for the proportion might actually differ based on the domains. So, for instance, this 80% rule is for employment practices. It may be different if you're considering housing allocations and so on. Now, of course, this is a controversial detection policy because it requires proportional outcomes independently of the non-sensitive feature distributions. Now, of course, this is what critics assail it for, that there exist scenarios where disproportional outcomes are justifiable. Now, of course, supporters actually point out that in some sense, if not for this test, there is no other way in which you could detect it. Now, this is like a test that captures many cases of indirect discrimination, but it might also catch a whole bunch of other non-discriminatory scenarios as well, but that's the only test that you could use to point out indirect discrimination. And then when you are actually litigating these cases, there is a provision for business necessity where you could actually show that it is necessary for your business to avoid being falsely accused of indirect discrimination. So, for the purpose of this talk, if the answer to the second question, can we detect discrimination in decision making? Well, so there are two tests that you could use to detect the discrimination. One is a situational test using inputs, and the second is a proportionality test using outputs. So now we get to the meat of the talk, which is how can we control algorithmic discrimination? Now, what do I mean by controlling for discrimination in algorithmic decision making? Well, here is the way we started thinking about this. So can we train classifiers that can pass both the discrimination detection tests? Meaning, if there are some tests for discrimination, then a fair, without debating whether the tests are justified or not, can we train classifiers that can actually pass the discrimination detection test, which is situation tests using inputs and proportionality tests using outputs? Now, if you think about traditional classifier training, you always try to optimize for accuracy in matching past decisions. And so we define what we call as a fair classifier, which should avoid both direct and indirect discrimination. That means it must not fail the discrimination detection test. Now, of course, in the process, you have to give up something. So you might have to give up some amount of accuracy. So our goal is to train the most accurate classifier that would pass the discrimination detection test. And that's the challenge that we have. Okay? So now, when you're thinking about, when we started thinking about, we started with a couple of straw man. Like we said, okay, let's try to control for direct discrimination first. Let's try to eliminate that. One simple idea would be you train the classifiers, but you train them only on the non-sensitive features. In the process, you try to maximize the accuracy in prediction, but without the sensitive features. Now, the good thing about this is that it eliminates direct discrimination. Because if you think about it, because the sensitive features have 0 weights on them, it would pass situational testing. But the unfortunate thing about this is this sort of a training actually introduces indirect discrimination. Now, to understand why, suppose you're training by stripping out the sensitive features. So there is a sensitive attribute in red, and then the others are the non-sensitive attributes. So during the training phase, suppose you stripped out all the sensitive attributes. Now, what the classifier will do is, because it is missing the sensitive attributes, it is still trying to match the past decisions as much as possible. What it will try to do is it will look for other non-sensitive attributes that are correlated with the sensitive attributes, and it will try to give them more or less weights depending on whether they're positively correlated or negatively correlated with the sensitive attributes. So essentially, learning algorithms will actually try to compensate for the lost data. And so if the blue ones are positively correlated with the sensitive attributes and the pink ones are negatively correlated, the values, then essentially you would end up, during the training phase, you'll end up weighing NSA1, the blue one more and the pink ones a lot less. So, of course, the only time when this wouldn't happen is if all the non-sensitive attributes are completely uncorrelated with the sensitive attributes. That's the only time when this would happen, when you don't have any issues. But unfortunately, oftentimes when we are training these algorithms, these days, it's always, big data is always considered a lot better, so we try to throw in as many features as we can for which we have information. And as a result, there is a very high chance that some feature or the others would be correlated with the sensitive attributes, and you would end up introducing a very intense form of indirect discrimination. So that didn't work out very well, our attempt to control direct discrimination. Let's for a second think about controlling indirect discrimination, separately and ignoring direct discrimination. So this would mean you would want to pass the proportionality test. So to pass the proportionality test, one simple idea would be to train separate classifiers for members of each sensitive feature group. And then you maximize the accuracy in prediction for each group, and then you select similar fractions of members from each group. Right? You train separate classifiers for men and women, and then you select similar fractions of them to be in proportion. In some sense, this is very similar to affirmative action or quota-based system. Now, the good thing about this is it eliminates indirect discrimination. It passes proportionality testing. The negative thing is it reintroduces direct discrimination, because now you have a classifier that is explicitly taking into account sensitive features. So here is the challenge. Can we control for both types of discrimination at the same time? And the answer is yes, and that's one of our proposals. So the question is, can we introduce or what we call as learning with fairness constraints? And the goal here is to express discrimination tests as constraints on the learning process and to optimize for accuracy and train the classifier to optimize for accuracy under the fairness constraints. So the key question becomes, how do you specify these constraints so that they can be solved efficiently for a number of different types of classifiers? So an example would be, how do you fair constrain a hinge loss classifier, which is the one that I was mentioning earlier, where you have a loss function that you're trying to minimize. This is the traditional hinge loss classifier, and how do you constrain it? So the trick lies in specifying fairness constraints. And at a high level, the way we define fairness constraints is we define it as limiting the cross covariance between the items, the data items, or the users' sensitive feature values and their distance from the classifier boundary to less than a threshold. Now, let me try to explain intuitively what this means through a geometric representation. So suppose you have non-sensitive features 1 and non-sensitive features 2. So we're considering only the non-sensitive feature space. Because if we consider the sensitive feature space, then all of a sudden you will be introducing direct discrimination. So within this space, so suppose the blue dots represent men and the pink dot represents females and women, and then they are spread in some space. Now, suppose you have a classifier boundary where all the things above the boundary line are picked and all points below the boundary line are rejected. What we compute first is, for males, we compute in some sense intuitively the distance from the decision boundary, which is the strength with which they were accepted, which is the green dot, the length of the green line, and then the strength with which they are rejected, which is the red bar. We add them up with negative sign for the red across all males, and we add up the same thing across all females, and our constraint is that the difference between the two should be less than some threshold. So similarly, if you consider another decision boundary like this, if you picked all the points on the green tick side of the boundary, then once again you measure for all men as well as for all women separately their distances from the decision boundary, which sort of measures like how well they are accepted into the class and how strongly they are rejected in the class overall. And you make sure that the difference between the two, that is the difference in the average strength of acceptance and rejections across different sensitive groups, stays within a threshold. Now, why did we introduce this form of a fairness constraint? The reason is actually computational. So if you think of a classifier, like the hinge loss classifier, then essentially introducing a fairness constraint to this would literally mean adding these constraints this way. And the nice thing about this, and this is the key point, is that this still remains a convex optimization problem, and it's very easy or it's efficient. You can efficiently find a solution to these problems, and that's the reason why this is interesting to formulate it this way. Now, we also implemented these constraints for other classifiers. So, for instance, if you take just to give you another example, if you take if you take logistic regression in its original form, you can just simply add constraints, fairness constraints this way, and once again, you can solve this convex optimization quite efficiently. So to quickly summarize what we are proposing for learning fair classifiers, which is we're talking about constraint training of a fair classifier so that it has no direct discrimination and bounds indirect discrimination. And our high-level idea is to optimize for accuracy in prediction without using the sensitive features to avoid direct discrimination, while also putting a threshold to bound the indirect discrimination. Now, it turns out that the way we formulated it actually allows us to optimize for fairness under accuracy constraints as well. That means you can interchangeably play this game and say, let me get in certain contexts, you might say, I'm not willing to take more than 10% hit in accuracy. What is the most fair classifier that you can get within that bounds of accuracy? Now, of course, the question is, do fairness constraints work in practice? Like, do these, because we define fairness constraints in a different way, would they actually lead to satisfying proportionality tests? Now, we checked this on a number of synthetic and real-world datasets. And the details are in our Learning Fair Classifier archive paper. If you just search for Learning Fair Classifiers, you'll find it. And the good thing is we found that by varying the fairness threshold C, which is part of our fairness constraints, we can alter the proportions of selected people in different in sensitive categories. And we also showed that compared to, I mean, there's a lot of other approaches that have been proposed in the last couple of years towards achieving these sorts of satisfying proportionality tests and to pass to situational testing. And compared to them, the interesting thing is we have, it gives a little bit better accuracy. Now, of course, to be fair, the bad thing about our evaluation is the evaluated scenarios that we're considering are not super real, in the sense that we're using real-world data sets, but it would be nice to see how this would play out in practice. So just to give you a feel for how it might play out, let me talk about two different scenarios. Let's take the first scenario of the diversity in college admissions. Today, a lot of admissions officers would like their college admissions process to admit a diverse body of students along race or gender. But the problem is increasingly, you cannot use sensitive attributes in your decision-making process. But if you think about this, the fair classifiers that we propose can actually adjust the weights, have the potential to adjust the weights on the non-sensitive attributes so that they would not so that they would actually be legal and still be useful to achieve the kind of proportionality that you would want in the process, in the admissions process. And similarly, if I can take a little bit more provocative example, you could also think of using fair classifiers to help diversify departmental hiring. That is, suppose you wanted to hire faculty with diverse expertise, right? So here I'm showing along x-axis the expertise somebody has in systems, and along y-axis the expertise somebody has in theory. Say the green dots represents Europeans and the red dots the Americans, right? And there is some difference in the level of expertise along different dimensions. Now, typically, if suppose in the past, say all the European academic institutions hired mostly people from Europe because they were the only people who were applying, then, and if that was your training data, and now you try to learn from the training data, of course you'll always end up picking a classifier that will emphasize theory more than systems expertise. Whereas if you used some sort of fair classifiers, you could actually force the decisions to be, the decision boundaries to be in such a way that they would actually admit more diversity in along the different hiring axes. So you could use fair classifiers not only to achieve diversity along sensitive attributes, but also along non-sensitive attributes as well. And that's the high order bit. Now, to summarize, and to talk a little bit about a couple of future directions that we're looking at. So I started off with three motivating questions. Can algorithmic decisions be discriminatory? And the answer is yes. And can we detect discrimination in decision making? There are some tests that are applied on both on inputs as well as outputs. And the question is, can we actually control algorithmic discrimination by the way of designing classifiers that would pass these discrimination tests? Now, of course, there's a lot of interesting ongoing and future work. The first thing that we're looking at is extending our ideas, which I described mostly in the context of binary classifiers, to multi-class scenarios and ordinal classification, which is actually turns out it's not that straightforward. And similarly, we are also considering cases of multi-stage decision making, where at least so far we assume that all the non-sensitive attributes and the sensitive attributes are available for the decision maker at stage one. But in real world, oftentimes you actually have a much more complex scenario where certain attributes become visible to you as part of the decision-making process. So for instance, when you get faculty applications, we decide to ask for letters of recommendations for only a subset of them, and only for a subset of those, we actually ask for on-site interviews and so on. So in the process, we're eliminating some people even before we had all the information about them. And thinking about fairness in those, in that situation is much more complex. In some sense, when we started working in this space, the key realization that we had is that the space of differential treatments that are based on sensitive features is actually quite vast. That means if you think algorithmically, or if you think from a perspective of learning frameworks, the number of different ways in which you could base your decisions on sensitive features is actually extremely vast. There are very, very intriguing methods through which you could differentiate between people. In fact, there are other works that looked at, instead of fairness constraints as we were doing them, there were others who proposed using regularization as a way of achieving fairness. There are others, like Cynthia Dwork, who actually had a completely different way of using fair representations, where they transform the data before they even make the decisions, sort of a thing. And I find this computational way of thinking about fair decision-making as fascinating. And of course, this is not to say that, that this is limited in the sense of once you understand the space of possible differential treatments, you'll still have to make the most important or a very important judgment call on whether the differential treatment constitutes discrimination in a particular scenario. And that's where it requires a social science perspective. Yeah. So to just conclude, in terms of the bigger picture, what we're talking about discrimination is just actually one aspect of fairness in decision making. And fairness itself is more broader than discrimination. And related to these things are, there are concerns increasingly about transparency of algorithmic decision making, which is about helping users understand why and how decisions were made. And there are people who are working on all these different perspectives as well. And of course, the one thing that I have not seen many people actually work on is actually the evolvability of these systems. That means, yeah, this is, if you actually use this algorithmic decision making, would you actually, would these systems actually stabilize in the long term towards some long-term goals? And that concludes my talk.
There is some time for a question.
Are there any egregious examples of algorithmic discrimination that you know of?
Egregious examples?
Yes.
Oh, there are tons, right? So, I mean, at least in New York Times, you keep hearing all sorts of examples. So, for me personally, the reason why I got intrigued or drawn into this was actually because of spam filtering, triggering sometimes. So, for instance, there was about 2 or 3 years ago, I moved from, I took the TGV from Saarbrücken to Paris, and then I logged into my Twitter account in Saarbrücken, and then I logged into my Twitter account in Paris, and it immediately blocked me and sent me an email saying there seems to be some potential attack on your system. What probably Twitter spam filter didn't realize was that you can go across 500 kilometers in less than 2 hours, kind of a thing. Of course, that's not a case of an egregious. It's not even a case of a discrimination because the set of people who travel on TGVs do not constitute a socially salient group, much less that affecting people in very fundamental ways. But in general, there is there's a lot of potential for these sorts of when you blindly apply algorithmic decision making and you train them to match some past decisions, there is always the danger of that happening. And in fact, I think John's talk was more talking about a real world scenario of judges and potential biases in their decision making.
Thank you. More questions?
Just a technical clarification, when you set up those constraints in the optimization problem, you're still in the setting where there is only one sensitive feature, and the rest are non-sensitive.
So you could do it for each sensitive feature, yes.
But that would be, you would write separate constraints for every sensitive feature?
Yes, so you could keep adding. So the nice thing is you can, because it's a convex optimization formulation, you can keep adding more constraints. So you could write one for each sensitive feature. You could also write one for like combinations of sensitive features. Like it means you could put a constraint on, say, African American women as a protected group, and you could just simply keep adding more and more constraints.
And you will have more thresholds. One.
Yes. So of course there is no free lunch because the convex optimization formulation, we'll start finding less and less efficient solutions.
Okay. Thank you. More questions?